Hello everyone, my name is Werner. I am an engineering manager at Coinbase. If you guys have ever heard of the company that buys and sells cryptocurrency, Bitcoin, Ethereum, stuff like that, that's where I work. I work on the crypto engineering team there. So I joined there about 2 years ago at the start of 2017. It was right around the time that Ethereum had just hit $15 and Bitcoin was about $600. And I had, when I joined, everyone asked me all sorts of questions. They were like, what's this thing? What does that mean? And every time I learned more about what cryptocurrency was, I just found more questions. So I thought I'd go through some of those today. Why does Utxo Consolidation improve coin selection? And anybody have any idea about half those words? Awesome.
Unconfirmed transaction outputs.
Close, unspent. We're going to get there. You guys are all going to know what that means by the time I'm done here. So, I work on crypto payments. We handle all the interactions with blockchain, and Coinbase currently has 750 people or so working there. We work in San Francisco, and we have $150 billion worth of assets traded between 20 million customers over 40 plus countries. We handle a lot of throughput. Our systems are regularly processing transactions day and night, and you need to be able to understand how the data is working under the hood to be able to support that kind of scale. We're going to talk about some of that. The mission of Coinbase is to create a more open financial system. And what that means is our current financial system is closed off to a lot of people. You need to go through a lot of steps to be able to access different types of capital. And there's a lot of research that shows that capital is directly tied to your well-being, your quality of life. And if we can increase access to that capital, we can make a great impact in the world. So you'll hear this a lot, that decentralization is the critical piece of cryptocurrency, and it's the kind of thing that unlocks a lot more use cases. When you're working with a credit card company, you're trusting that credit card company to make that payment for you, and the merchant is trusting that credit card company to give them the money that they deserve for giving you the goods. When you send your landlord rent through an ACH payment, you're trusting the Fed to make that change between the different banks, and we can create a system that does not require that trust. It's not that we shouldn't be trusting them, but if we can do the same thing without needing to trust an organization to facilitate it, it's a great outcome. So, cryptocurrency is the first, Bitcoin is the first and most prominent network of cryptocurrency assets in the world. It's probably the one most of you are familiar with. And there's no organization that facilitates the transfer of Bitcoin from one person to another. It's done through a system of connected nodes in a network that is able to move the authorization of spending that Bitcoin from one person to another without any one party saying that needs to happen. Bitcoin, what we're going to find here as we get into these questions is, now if I start talking about miners, we can start talking about how miners produce blocks, and we start to find out that these questions get way deep. Like, you could get really technical with this stuff, and literally everything on here are real things. Like Mimblewimble and Grin and ZK Snarks are some of the most exciting new technologies that are out there. Like, cryptography has had a resurgence. Like, this is a renaissance for cryptography because these cryptocurrency networks exist. A lot of the, ZK Snark stuff, zero knowledge proofs, that stuff was around in the 80s, and we're finding good applications for it today to do amazing things like the new Grin currency. There's awesome stuff happening. It's really cool, but we have to focus our conversation to just one thing. We're going to talk about Bitcoin transactions today, because This is how you are able to operate a wallet at scale. So let's get into the transactions. The transactions represent a simple exchange of value. When you have a Bitcoin transaction, it has a certain set of parameters that you're going to say it's going to be this amount from this address to this address, and just the basics of what you need to have to be able to execute that transaction on the network and have it go through correctly. When you specify where the amounts are coming from, you're specifying the outputs of previous transactions. And you can only specify unspent outputs, and that's why we call them unspent transaction outputs, or UTXOs. And UTXOs are kind of the basis for how Bitcoin forms their transactions. So this is your basic transaction. You have any number of inputs and any number of outputs. And this is really flexible and nice because you can start grabbing different inputs that you have and of varying sizes, specify all of those are going to be combined into one transaction. And then when you send them out, you can specify any number of outputs to any number of destinations that you like. This is super flexible so that you can do things like having 5 different people send to 5 other people that have nothing to do with each other through this thing called transaction batching. It's very flexible. It's not like a bank account where you have to pull from one person's account. You can pull from all sorts of different accounts to satisfy a send request. You'll notice the bottom one there is the change output. This is when you have a little bit left over, you usually send the rest back to yourself. And I'll show you what that means. So on this transaction, you have to pay a fee to get it processed. When you broadcast the transaction to the network, you have a little bit extra that you give to the computers that are processing your transaction. So you calculate that based on the size, like the bytes of your transaction. So that means the more inputs you specify, the more outputs you specify, the more data you put into that transaction, the bigger space it takes, the heavier it is, and the more you pay in a fee. So the way we calculate this is the fee rate in sat per byte, or sat a byte. And say we pay a 1.02 sat a byte transaction on a 225 byte transaction, you'll pay 0.018 cents depending on the price of Bitcoin at the time. So when you post that and you attach the feed and a miner sees your transaction and processes it, it will run through a script that will move the authorship or the authorization of those inputs to the person you're sending it to. And every time you get a block after that transaction, it's called confirming your transaction, which means that essentially you can be sure that that transaction isn't going to get reversed. So I'm sorry with the small print if you're in the back, but this is a screenshot from a block explorer. This is just data from the internet, and it represents what's actually in the blockchain. And you can see here, this is pretty standard. You'll have these inputs here. These are all different hashes, and each UTXO is represented by a hash. They have an amount on them, like 0.0869, 0.021, 0.0998. All those combined together to one output that's 0.501 Bitcoin. You can see at the top, they've paid a fee of 0.014 Bitcoin with 1558 sat a byte with a 930 byte transaction. You can see this one, the size is much smaller, and they paid about the same sat a byte. And here you can see the 6 inputs cost $124, one input costs $30. And they just paid way more than they needed to on that transaction. So here, you can see at a different fee rate, they were able to do the same thing with a 1.25 sat a byte, and they get paid 10 cents because the fee rate will fluctuate depending on how much volume is going through the Bitcoin network. So the same kind of thing here, kind of broken down. If I have these 4 different inputs and I have the keys for each of these different UTXOs, and so you'll see, okay, 40.21.43 total in my wallet. I can say, I want to send 0.4 Bitcoin to someone else. Actually, I want to specify these 2, It'll have 0.4 Bitcoin on it. I'm only going to send 0.34 to someone else. 0.05 is going to come back to me in the change output, and there will be a 0.01 Bitcoin fee on that transaction. And this is a pretty standard basic transaction. And here you can see one in the wild where they had a 1 input, 7.2 Bitcoin UTXO, and then they sent 2 to 1 and 5.2 back to themselves, most likely. And here, if you have a lot of smaller pieces, you can do the same thing. This is the flexibility of the UTXO model. You can just grab a whole bunch of inputs to sum to a larger amount if you don't have any one that's big enough. So if you take the 0.34 Bitcoin that we sent in the last transaction, after a few confirmations, meaning a few blocks show up in the blockchain, then we can use that for the next transaction. We can do 0.34 Bitcoin into this one. Same thing, we send 0.24 to someone else, 0.09 comes back to us, and all these values are arbitrary depending on how much you want to be moving around at that time. And this is how Bitcoin transactions work. Any UTXO models will work this way, so Zcash, Litecoin, Cardano, anything like that. So this seems pretty straightforward. It's like a change drawer. You can grab a quarter, grab a dime. It doesn't seem too hard. But in this case, we process a lot more transactions than what we're talking about here. These are like one by one. We can process in the range of hundreds or thousands an hour. So we need to be able to be very sure of what we're grabbing and very sure that we're sending the right amounts to the right places with the right fees. Because with this kind of stuff, if you're off by a few cents and you're doing high scale, you can easily spend $1 million or more. So this brings us to this story of the hot wallet. The hot wallet is a pool of UTXOs. And you can think of it like the front of the bank, where you come in and you want to get to some money, and we don't have all of our funds sitting in the front cash drawer. We have it in the vault. 1% of our holdings are in the cash drawer, and this satisfies the throughput that we get from a daily basis. And this we call our hot wallet. And that hot wallet is really a database full of the addresses that are the UTXOs that are available to us for keys we control. That's a mouthful. We have a database that represent all the keys for the Bitcoin addresses we've generated. We have those with the amounts associated available to be spent as UTXOs. When we select the different UTXOs we want to use, we call that coin selection. And coin selection is a topic of a lot of research, and it's a very deep topic in and of itself. Essentially, this is the equation for coin selection. It's essentially a subset sum problem. It's really not that complicated. You have an array of values, like the amounts. You want to select the items in that array that will equal the amount you're asking to send plus the fee. And the more accurately you can do that, and the more efficiently you can do that, the higher throughput you can support, and the lower fees you pay. So you have a direct benefit to being able to be good at this. So this is more like what we have. You have a whole bunch of random values. It's not just 4. We range anywhere from 30,000 of them to, we had millions at the end of 2017. And selecting these, and when you have that large of a set, can be challenging. So you have to have really good SQL queries and really efficient database indexes to be able to find the values you need to specify for the Bitcoin transaction that you want to send. So you have this kind of Goldilocks problem where if you have too many small UTXOs, you're specifying a whole bunch of them as inputs, and you have a huge transaction for each of your send requests. If you have too many big UTXOs, then you don't have much throughput, meaning you're waiting for that UTXO to be confirmed in the blockchain before you can use it again. So if you have these enormous UTXOs of like 1,000 Bitcoin, or you have 0.0001 Bitcoin UTXOs, both are pretty useless. So what you want to do is you want to craft your UTXO distribution to match the average size of the send request that you're processing. So how do you do that? There's 2 different strategies we can take. One is called UTXO consolidation. and the other is called change splitting. We'll talk about UTXO consolidation first. We're going to talk about change splitting first. So change splitting is breaking down large UTXOs into small UTXOs. And this we most normally do when we do a restore from our cold storage. Our cold storage system will drop a very large UTXO into our hot wallet, like one place that has a very large balance. And then we process that by satisfying a send request. We specify a lot of outputs of a smaller size that we will then break up again on subsequent confirmations. And it looks kind of like this. Say we have a 129 Bitcoin input, we'll just do one of those, and we'll specify a whole bunch of outputs. So we kind of just open up the pipe, and we start to have a whole bunch of more reasonably sized UTXOs to select from for other Bitcoin transactions. And then we do it again. And you keep change splitting down to a point where you have the UTXOs are roughly the size of the types of send requests you'll get, and you've evenly distributed those UTXOs out. We have a system to just automatically do this. We just configure the size that we want and how many we want. And you can see this in the wild. Someone had a 1,091 Bitcoin transaction, and it's like $5 million, and it'll break down into a whole bunch of same-sized UTXOs, and they're just change splitting when they do that. So UTXO consolidation is just turning it around and going the other direction with it. So this one will take a lot of small UTXOs. We call it dust, which is essentially very small amounts on the UTXO, and we consolidate into one reasonably sized UTXO. And we actually hadn't been doing this much in 2017 during the run-up, and it was a concern of ours because you can get into a situation where the amount on the UTXO is smaller than the cost it will be to add it as an input on the transaction. It's literally unspendable because you'll spend more money using it than it's worth. And if you have too many of these, you can actually have a lot of value locked up in these small, unspendable dusted inputs. So what you do is you do this, you set the system up where you can configure it to say anything below this dust line that we consider unspendable. When you get a chance, make a transaction like this to combine all those with the same transaction, and then give yourself one change output to just make a reasonable sized UTXO. And then you have it monitor the fee rate of the market. So when things get cheap to broadcast Bitcoin transactions, you do a whole bunch of these to clean those up, because if the fee rate goes down, it unlocks those UTXOs to be spendable because you're not paying as much to use them as an input. And you can see that being done here, where you have a whole bunch of these really small ones, and it produces one Bitcoin sized one. So, why does UTXO consolidation improve coin selection? So you turn a whole bunch of really small dust into one usable UTXO. So, normally when I give this talk, it's like 30 minutes or so, and Mike said I should do 30 minutes more. So I was trying to think of what I should talk about, and I thought I wanted to challenge the room a little bit more to talk about an advanced topic. And I tried to think of what is hard mode for hot wallets. I don't know if you're familiar with what a Bitcoin fork is, but we're going to talk about a question related to Bitcoin forks. They can be daunting because there's a lot of things at play, but we're going to try to explain one because it's fun to talk about. So, a new question: how can you leverage miner rewards to protect against free play attacks? There's a lot to unpack here. So we'll start with what is a fork? So if you're familiar with GitHub or software development, Git is a version control system that allows you to commit new code to your repository in a sequential fashion that builds on the previous commit. And it looks kind of like this, where you have some hash of your commit here, and you build on it. And this is just standard practice for software development. So you can also have different directions at the end. You can take that 0F9077, it's a representation of the code at that state. You can split it into two different paths. You can merge those back together with diffs. This is just how you develop code. And this is called a fork. You can see like there's even a fork button on GitHub where you can just easily click that button and create your own version of this code. And this is a common idea in software development. And we can apply it to cryptocurrency as well, because we have sequential blocks that we reference with their count. So we call this the block height. And this is actually a timely or a notable height for Bitcoin, because at 478,558, there was a major fork that happened on the Bitcoin network. It's a network called Bitcoin Cash. So this is a different Explorer from the one before, and again, I'm sorry about in the back, but there's a few things that I want to point out on this. This is all of the data that you can know about this block on Bitcoin. You can see Bitcoin 478,558, and this is all the data that is related to this. So it can talk about all the inputs, talk about the number of transactions. This is the miner, btc.com. It happened on August 1st. It was a very early morning for me that day because we had a lot to prepare for. And the hash. So the hash is, they take all the transactions, they put it in the block, they run it through a hashing function, and with a nonce, and it produces that value. And all the computers that are trying to find the next block are doing this with a whole bunch of different nonce values and different transactions. They're looking for a hash that starts with that many zeros. That's called the difficulty. So this is deterministic to be able to produce blocks every 10 minutes or so. So what happens is all these computers are just crunching all these transactions, trying to run them all through hashing functions, trying to find a hash result that starts with that many zeros. And when they did, they found the next block. And this is why hashing power matters. Because the more hashing power you have, the faster you can calculate that value. You find the block, you get the reward, and then everybody starts building on that block because they want to have the most time to find the next block. So that was the hash. That's when it's mined. That's the miner. And you'll also notice over here the size and the version. Don't really need to know what number that is exactly. You just have to note that ends in 14. That's good enough. So, now it's the nonce they used, the Merkle root, which represents the previous block, all that kind of stuff. So this is kind of what it looks like, where Bitcoin went along to 478,558, and on that block, Bitcoin Cash forked into their own network. And when that occurred, both of them found their next block, and 559 was different. Those are two different blocks that were stemming from the same 558. And you can see that, we look at here, this is 558, was at 1316 on August 1st, 2017, under Bitcoin Cash. And you can see Bitcoin had the same, right there. They're sharing the same block. But you'll notice a different number of transactions for Bitcoin Cash. And here, they had 6,900 transactions. The version number is different, and it was about 5 hours later because the difficulty for Bitcoin is really high. It took a long time to find the first block for Bitcoin Cash. And we look at Bitcoin's 559 block, 472 transactions was 10 minutes later or so, and their version was 14. So what do we know about this? Bitcoin Cash was a hard fork. It meant to split the chain. And it accomplished that by changing the version number over there and some other magic to be able to make the transactions that happen on Bitcoin Cash completely distinct from Bitcoin. Meaning the data that you're broadcasting in your transaction will be rejected if you tried to broadcast that same transaction on Bitcoin. And that's important because with a hard fork, this is relatively straightforward. They said they went to the Bitcoin GitHub open source, forked it. They made some configuration changes, most notably larger blocks. If you're familiar with the Bitcoin drama of 2017, Bitcoin Cash is all about larger blocks. Bitcoin wanted layer 2 technology. It's a whole ordeal. But Bitcoin Cash said, we're going to create larger blocks. We're going to go our own way. And they created Bitcoin Cash. And they said, we're just going to split the chain and create a new blockchain. There's a lot of drama about Bitcoin Cash. But what you need to know is that that was a hard fork. So what is a soft fork? Recently, there was a fork of Bitcoin Cash. The difference here was that this fork, both sides thought that they were the original currency. They weren't creating a new chain. They had a difference of opinion in which way it should go, and they both thought that they were the coin. So how do you determine which one is actually the correct coin? Because they said, well, we're going to change these parameters. They said, we're going to change these parameters. And it's something dumb like whether or not there's a scripting language in it or something like that. Like, they get really caught up in the tiny minutiae of this stuff, and it's bitter. Like, they spend millions and millions and millions and millions of dollars fighting over this. And they both think that they're Bitcoin Cash. This is called a soft fork, where when you fork and you make a change, you are backwards compatible with any other blocks that are happening. So they're not changing their version number, and their transactions will work on either side of the chain. This really gets confusing, because now, if I go to Bitcoin Cash and I send 10 Bitcoin Cash to someone else, that transaction is valid on the other side of the fork. But it's not over there, because I didn't broadcast it to that side. So this gets us into a few issues. You'll see here, this is Bitcoin Cash's 767 block. They have that same 12 version. If you look at 767 for Bitcoin SV, same version number, but the hash is different. So this is a problem, because now we have two different sides of the blockchain that have different states of the world. And I broadcast a transaction to one of them, and the same keys that are on the other side are still valid, and they exist. And this is why you get an extra currency for each anytime a fork splits. So this puts us in a tough spot, because the network is super unstable. If someone comes to Coinbase and is like, I want to send 10 Bitcoin Cash, we don't really have guarantees around whether or not this is going to do what they expect it to. So we paused Bitcoin Cash transactions when this happened. It was what they called a hash war, where a few individuals on each side booted up a whole bunch of computing power and just tried to get a longer proof of work than the other side. And they literally went down this path and tried to beat the other side in getting more blocks. And they were going to do a 51% attack to try to wipe out the other side. It cost a ton of money to a lot of people. It was, it's really unnecessary. But this was the drama of late 2018. And what came out of it, well, they're two separate chains now, Bitcoin Cash and Bitcoin SV. Both sides were like, we're Bitcoin Cash. It's hard to talk about this stuff without getting into the politics of it, because Bitcoin SV was this kind of like, I feel like this should be done differently, and they explicitly stated they were going to attack Bitcoin Cash network, which doesn't seem like a good community thing to do. So long story short, there's two different coins now, And Coinbase providing access to one side of that chain is very challenging because anytime you transact on either side, you need to be able to protect those funds from the other side of the chain. The reason why I say that is a thing called a replay attack. So if Alice is sending Bob 1 Bitcoin Cash, this is the same coin selection we talked about earlier. You have these inputs, and 1 Bitcoin Cash goes to Bob. The remaining 0.08 comes back to the change output, and you pay a small 0.02 Bitcoin Cash fee. So what happens is Alice broadcasts this to the Bitcoin Cash network, and it sits in the list of transactions to get processed. The miner processes it, and it goes through to Bob. However, that transaction is a signed, broadcast to the world copy of saying, I know how to move money from these inputs to Bob, and I signed it, and it's all good to go, and it can get processed. And because Bitcoin SV shares the same history, there's no way for Alice to stop Bob from broadcasting that on a different network, on Bitcoin SV. So Bob could do that, and it could get Alice's BSV sent to him as well, even if Alice didn't really intend for that to happen. And this is okay. I mean, it's not necessarily bad. Like, Alice can just send herself some funds, and then she's good. Like, you can send it from there, and like, you have a new hash that isn't stemming from the shared history. But this becomes a problem when you're an exchange because of the hot wallet. So with the hot wallets case, again, we go back to the same list, and when people send Bitcoin into Coinbase, these different UTXOs were just outputs that they provide to us from a previous send that we can now use to coin select for send requests going out. We don't allocate one send request to one user or one UTXO to one user. So if you send 1 Bitcoin into Coinbase, that 1 Bitcoin might get used for someone else's transaction somewhere else. But that doesn't mean that you have any less Bitcoin. We just pool the funds together. And the reason why is because we have 20 million users on Coinbase. If we all had their funds sitting on the addresses that they own, we would have billions of dollars online, and that's incredibly risky. So we keep a very small amount of pooled funds to satisfy any certain requests that come along. This creates a problem because, say Craig wants to send 10 Bitcoin Cash into the exchange, and then they send 10 Bitcoin Cash back to their own wallet, and then they replay that transaction on Bitcoin Cash or SV, and then they do it again. And what happens here is we credit them the 10 Bitcoin Cash when they come in, and then they can send 10 Bitcoin Cash to themselves, and we deduct that. But then they also replay that on the Bitcoin SV network, and they start to drain our hot wallet of all of our Bitcoin SV. And this can be done in any soft fork that happens on any network that we support. So we have to be very sure that if we are going to allow them to transact with either of these currencies, we have some way to prevent them from replaying that transaction. So there's only a few options on how we might be able to do this. Because in order to interact with Bitcoin Cash, you have to be able to create a transaction, sign it, and broadcast it. So we can't really change how that works. We just have to change something about one side of it. But they're a forked currency, they operate a lot the same. You start to kind of need to rack your brain around how this might work. And we get into dust mixing. So dust mixing is a strategy that we had to implement for Bitcoin SV. And it's pretty much the standard for how you can solve this problem. And in fact, like, a lot of exchanges will actually cooperate in order to make this work because it's just a common problem in the industry. What happens if we go back here to the Bitcoin SV fork, and at the 766 block, the fork occurs, and they go their separate ways. So if we looked at the Explorer from before, Bitcoin.com got the miner reward for the Bitcoin Cash block, and mempool.com got the Bitcoin reward for the BSV side. And when you get a reward as a miner, this is just funds that are created out of thin air and credited to your address that you specify when you find the block. It takes like 50 blocks or so in order for that money to land. And so Bitcoin Cash, the Bitcoin.com miner will get 12.5 Bitcoin Cash for finding that block at that time, and they'll receive it a while later. So what we can do is contact that miner, talk to them, say, look, this is our issue, we've got replay protection that we need to implement, and we can get one of those Bitcoin from them, one of those Bitcoin Cash. And if we can have them send us one of those Bitcoin Cash, we can do chain splitting, and we split it down to a very small amount. So we explode that UTXO, and we create a whole bunch of dust out of it, and that's to create a lot of very small pieces of a Bitcoin Cash that doesn't exist on the other chain. So this has to happen after the fork, because we want to have inputs that don't exist in that world. So when we do that, now we have this tiny little piece of extra dust that we add as an input on that transaction. And this allows this transaction to not be possible to exist on the other side of the chain, because this Bitcoin Cash doesn't exist on that side of the chain. It was never created because the block reward was never granted on that side. And this mixing in of dust allows us to produce a transaction that if you were to replay it on the other side, they wouldn't know, like the node wouldn't know how to process it. Like you're specifying money that doesn't exist, and it rejects it. And this is great. So this, when we broadcast it for Alice, it goes to Bob, and Bob tries to replay it, it just doesn't work. And it should be noted that this is unidirectional, so if you implement it for Bitcoin Cash, if you create a Bitcoin SV transaction, it could still be replayed on Bitcoin Cash. So you have to get dust from both sides, and dust mix it in. It's also good to note that because of the way that you are using these UTXO models, any outputs that come out of this are also what we call tainted now. So the tainted UTXO, you can just use it freely. So when we mix in the dust, it really just takes a little while to churn the whole hot wallet. You get some dust mixing in, all of the UTXOs in your hot wallet get tainted, and now you don't really need to dust mix anymore. It only takes a little bit. So, how can you leverage miner rewards to protect against replay attacks? You can get the reward and break it into a whole bunch of small pieces, mix it in, and it helps you stop any kind of replays. Thank you.